So yeah, thanks for the introduction. Thank you for inviting me. I'm very excited to be speaking to you all about some of our works going directly from electron microscopes to atomistic simulations. So my background is in first principles computations, particularly in density functional theory, molecular dynamics, combining with traditional machine learning and neural network with statistical approaches. And then when I joined Oak Ridge as a postdoc, I also started working on utilizing these as well as understanding experimental microscopic images on variety of material systems, complex oxides like perovskites, 2D materials like graphene, iron germanium like magnetics, and then also organic side of the story, polymers and molecular crystals. Interest and also sort of the focus of the talk would be around construction and implementation of the physics-based machine learning, deep learning frameworks. How can these be interpretable and extensible, as well as some of the causal mechanisms that may exist. And all of these efforts are really tied to this big concept of automated experiments. And there has also been a lot of efforts going on at Argonne National Laboratory, where we all want to understand and combine the theory and experimental knowledge. And this almost sort of seems like a childhood fairy tale, right? We want to go from the observational data, we want to perform atomistic simulations, going back and forth, there and back again, from the misty mountains to the mountains, going to reaching the goal. And there are so many paths, and there are great papers coming up showing those constructing how to go from microscopic data to understanding how this all work. And that's where I come in. I just don't want to follow all the paths that are being constructed and discover. I also want to understand why things happen. And that's what you would probably be hearing as sort of the theme of this presentation today. So first off, I would start by giving you a couple of deep learning frameworks that we have developed going directly from microscopic data to atomistic simulations. On the passing, I will very briefly mention about some of our additional efforts on reinforcement learning for electron beam physics, and then physics-informed Bayesian optimization methods for active physical learning. And then the second part of the talk will be learning about causal machine learning. And just a human perspective, we tend to understand correlation and causation all the time and mix them up. So I like to give this little example of something like day-to-day basis activity. So if I say, I feel more productive in the evenings than during the day, this could be affected by multiple reasons, right? How many cups of coffee I have had in the morning, how many meetings I have had, how did the call go with my mother who lives in a different time zone. So there are so many causes there, but however, I cannot really establish a direct cause-effect relationship. Because I cannot say directly this particular cause is affecting this outcome. However, if I strictly explicitly say that I turn off my phone today and nothing can distract me from work, this is causation because me turning off my phone is causing directly to focus. So this is sort of a causation relationship which goes even beyond the correlative nature of all machine learning models that we are so familiar with. We want to understand if we can introduce this type of mechanisms in understanding both experimental data or simulated data. And the example I will show you today would be focused on learning about a problem on cation ordering on double perovskite systems. So let's just first get started with the deep learning frameworks, and then we will move on to the causal part. So in general, STEM measurements or STM measurements give rise to highly reliable structural and spectral data. That means there is a wealth of information on material structures and functionalities that are available to us. And these also create a great platform to build deep learning models for finding features, learn about scalar functional quantities, construct chemical or structural space maps. So this is how sort of the overall workflows of machine learning or deep learning frameworks look like. You have some sort of data set. It could be experimental data or simulated data. You have the training test, and then you also have the validation. Each time it is extremely important when you're mostly considering the models that are constructed on simulated data. In terms of experimental data, we would understand as well that this is not only having access to a lot of image-based data or a lot of experimental data, it also has to deal with how good of the labels do we have access to. So if we do not have access to some sort of a ground truth to compare our prediction with, that becomes very difficult for us to even test the validity of the deep learning frameworks that we work on. Now, generally, when we think about this noisy experimental images coming from the STEM or STM measurements, we are after identifying features such as atoms or defects. Generally, we have seen that the unit type of models typically work very well for noisy data. These accomplish two goals. One, removes noises, and then second is the neural network output, as you can see here, which is a semantically segmented map, has all the information about different atom or defect types. So now that we have access to all of this experimental data, are we done? Well, no, there are lots of challenges utilizing the image-based data. So just realizing the fact that performing imaging or characterization measurement is not enough. When we try to understand this sort of observational data, we are thinking about the instrument specificity, which relates to the aleatoric and epistemic uncertainties in the data. There is also implementation complexity rising from the different data formats and the large volumes that those come in. The next big challenge is the transferring information directly from experiments to theory, which means we need to address challenges like disparities between the timescales. So think about how long does it take you to take, let's say, a few images of a graphene using a STEM, and how long would it take me to perform geometry optimization of a 2000 atoms graphene supercell? Then there consists of fundamentally different latencies associated with imaging and simulation. Feature finding, regions of interest, identifying them is also very challenging. Then scaling up to perform those feasible simulations and performing these workflows on the fly end-to-end. And then finally, testing the reproducibility and extensibility of these workflows to other physical scenarios. So these are sort of the challenges we have to deal with. And that's where Atom AI comes into play. It's a Python-based infrastructure, which we have developed at Oak Ridge, tries to bridge between the instrument-specific libraries and general physical analysis. And if we compare the capabilities of Atom AI in terms of its functionality, ease of use, and instrument specificity, this is where it stands in terms, if we compare it to machine learning packages like TensorFlow, PyTorch, or the instrument-specific libraries like Py4D, STEM, Neon Swift, and so on. And today, the couple of deep learning frameworks that I will be talking about are based on the Atom AI platform. So the first one is the ELIT, Ensemble Learning Iterative Training. Why do we need another framework when we already know that the deep learning strategies have been very well established to categorize, let's say, natural images? So they are performing a classification task. Like we want to also perform classification, but our job is to identify atom, particle, and defect. So any image you take, every pixel should belong to one atom or one particle or one defect. That means we are trying to find nearly identical objects. There can also be significant variations in image acquisition parameters between different experiments or conducting different simulations. Now, there are a couple of ways we can think about. Let's try to just condense them into one and have this broad distribution of data and then train this neural network. Well, that may fail to recognize subtle features. And the second way is to, let's say, train every time a deep neural network, we have new data coming in, which is also not feasible. There is also data set shifts and out of distribution drifts, which are available. That means feature finding is very much challenging for this type of cases. That's where ELIT comes into play. we start by constructing a data set based on the simulated data. So it could be molecular dynamics or ab initio MD data. Then we have the ensemble learning framework. So we train multiple models. And then we apply this to the experimental data, understanding the fact that this may only be able to partially reconstruct the features, but then that gives us a good baseline to refine the training set, retrain the ensemble, apply it again to the experimental data to get to the robust feature finding, and then quantify the uncertainties associated with it. This is sort of a representation of the data set. We start from a 200 atoms graphene supercell, and in every simulation, we take out each atom and then perform it again. Once we have all the ab initio MD data, then we augment each of these frames, sort of. And then the idea is this looks like almost like a STEM image. And then the ground truth is the semantically segmented map, which almost looks like this, has the information about all the atom positions and the types. Next is we utilize unit type of model, which is shown here, the architecture. So again, the input is a noisy image. It could be experimental image or a simulated image. The output should be the semantically segmented map. So here is also the steps to the algorithm, where first we start by training this ensemble of models, apply it to the experimental data, choose an artifact-free model. So that's where human in the loop is coming into play. And then we redefine our training set, perform this in an iterative manner to get to the robust feature finding. Now, this has been implemented in multiple times, and you can access this openly through my GitHub page. So please look it up and try to, if you find it useful, it would be great. So today I'm going to show you some results on the graphene data, but I just want to quickly mention that this has been working remarkably well on other 2D materials and even on organic systems like finding protein nanorods. So, all right, so let's get to the results. Here are 3 different representative frames of the graphene STEM data. And then first set of models are shown here, the results where we apply these ensemble models that were trained on the simulated data to the real data. And we can see that only some of these features were reconstructed and found, and some of these regions are, we couldn't classify them at all. And that's what we were expecting. So in the next iteration, we redefine our training set and then also introduce the multi-class segmentation mask such that we are not only identifying all the carbon atoms present in the system, but also the impurity and the defect types. We are also estimating the uncertainties in the ensemble prediction on the level of individual pixel for both the carbon and the impurity channel. Now, very interestingly, this has now been implemented on the fly. So you can see Kevin is our rock star. He knows how to shoot electron beams. I don't. My code works on the background, and we can see that all of these features are getting recognized on the fly with great certainty. And then this is another sort of the images that I wanted to show where this is going on. This is where Kevin is again taking the graphene image data, and then we can again find the graphene rings, the 5-member or the 7-member rings, and how they propagate through the material. So in summary of the ELIT framework, we can iteratively identify the features. There is out of distribution drift in the data, which often limits the wide applications of deep learning models, and that's where ELIT is trying to help. And we are going from, from the high resolution STEM images to go to robust feature finding, as well as quantifying the uncertainty associated with our predictions. And I have shown you example how ELIT can also be implemented in real time. Again, if you're more interested in the technicalities, I'll refer you to the publication or the GitHub repository, but you're also welcome to ask me questions later on. So now let's say we have access to all of these features, like we know atom positions, atom types, and so on. What do we do with it? Well, my simulation background comes in, and I'm like thinking, is there any way to directly pipe in the STEM data and the features that we just learned into simulations environment? Well, there are multiple roadblocks. So first roadblock was just been addressed by ELIT, which is the feature finding. The next is, how do we identify the regions of interest? We are addressing different latencies, as well as the disparities in the length scales. So this is where the second workflow comes into play, where we build object, or this is embedded object, we call it, which can be readable by commonly utilized MD or ab initio MD packages like AAC, LAMMPS, or VASP. And then we utilize this object to perform structure optimizations on some of the regions of interest that we pick. And we are working on automating this process as well, which is an ongoing work, and I'm probably not going to show or have the time to show the results of. And now, once we have access to these objects, then we can perform molecular dynamics or ab initio MD or even DFTB for geometry reconstruction, or even going above, looking into, let's say, temperature-dependent dynamics. So if I heat up the system sequentially, so here I'm just showing you two different results from the ab initio MD performed at 300 Kelvin and 4000 Kelvin. We can see some of these atoms reconstruct themselves into forming Stonewall's defect. Now, interestingly, we can also track down all the uncertainties, because there are multiple steps to this workflow. We are going from images, then we are having deep learning, and then we are having simulation. So we can track down the displacement of atoms, bond lengths, angles, and then these can be compared to quantify uncertainties at each step of the framework. And we can also perform additional simulations to explore, let's say, dopant effects or the graphene healing effects, and which are essentially some of these could be observed even under electron beam. So the idea is, once we learn from these atomistic simulations, we want to utilize this information and send it back to the experimentalist to guide the next set of experiments. So that's sort of the summary of this framework, where we are going from ELIT to simulation, sort of the first step towards direct on-the-fly data analytics and experiment augmentation in STEM by utilizing DFT and MD models. If you are interested in performing this as well, you're welcome to, again, check out the open access notebooks. We understand that this is highly non-trivial, and there are extreme disparities in some of these, plugging into GPU versus CPU resources and making them scalable is something we are still working on. However, I have shown you an example where an end-to-end workflow can still be constructed, let's say, to study a few instances of graphene physics, where we start from a microscopic image, and then we can perform simulations with the help of deep learning. We also, for each of these deep learning and ML frameworks, we are very much aware of the FAIR principles, and so we try to adhere to these principles of how it could be more open access and reproducible and reusable. So thinking about as like portability along the way. So that's sort of the first part of the talk, and I mentioned to you that I'll talk a little bit about the additional efforts in terms of reinforcement learning for beam-induced physics, let's say. So because there is a very great effort in terms of understanding how reinforcement learning could be utilized to, let's say, for one particular problem of we want to understand where silicon dopants can form trimers, or the clusters could be formed. And this is one of the examples where we have looked at introducing a molecular dynamics environment to adjust dopant phenomena, dopant momenta, such that they can stick together towards pre-chosen sites on the graphene lattice. In this work, we didn't essentially take into account of the electron beam effect in general. However, we are working on multiple other environments which would be more appropriate in terms of taking care of the interactions and these electron beam physics that is involved. And the next set of additional efforts I wanted to just briefly mention is this Bayesian optimization for active physical learning. So in general, why is this important? because any scientific study you're thinking about, so you're performing a neural network, you're performing machine learning algorithms, all of these require search over broad parameter spaces. Now, conventionally, this has been done with grid search method, which could be time consuming and laborious. So Bayesian optimization could be helpful. However, the problem with the Bayesian optimization is it does not let us incorporate any physical knowledge. So that's where our new frameworks come into play. We are still following the general Bayesian optimization framework, where we start from the prior data that goes to posterior distribution. We select the next data, evaluate it, update the prior knowledge. But then here we have two different strategies that we play around, one with augmented Gaussian process, and then another with the reward-driven acquisition. So here is an example why this augmented Gaussian process is cool. Because let's say I want to model the magnetization from a 1D Heisenberg model. And then you can see if you just utilize the normal Gaussian process, we cannot model the behavior along the transition temperature. However, if we introduce this augmented Gaussian process, it can very well model the magnetization along the transition region. So we have tested the performance of this standard GP and structured probabilistic GP as well. And this has also been implemented for the 2D Ising model case. And the next set of strategy is the reward-driven acquisition, which essentially lets us even allow to compare the performance of different models. So let's say in the Bayesian optimization, you have the standard GP, you have the probabilistic model, so the augmented GP, and maybe this augmented GP was augmented utilizing 3 or 4 different probabilistic models, and we can utilize a reward-driven strategy to pick every time which model has performed the best, and then query the points in the next iteration in every optimization cycle. And I have implemented this on even real material systems like ferroelectrics, and this is an example on an iron germanium system where the excitation energies are directly related to estimating, let's say, the magnetic interactions like the DM vector or the J's. And traditionally, we would do this by atomistic simulations or expanding the model Hamiltonian, and there are multiple parameters associated with it. So if we can construct, which we have done here, a parametric model that would include all of this information, then we can even predict this excitation energies for a certain Q vectors, let's say along a specific direction, without the need to perform this atomistic simulation or constructing the model Hamiltonian. All right, so this is sort of the first part of the talk. And then the second part was, of course, the investigating the causal mechanism. So why causal? Again, all of these machine learning, deep learning frameworks that I just told you about, these all are dependent on the correlative nature of the models. So can we do better? Because if we just say that some of these features are related to this target property, that's not probably enough. And why is this so? Well, the bit of motivations is when Yantao, Maxime, and Sergey were working on this PFM data, and they were looking into how under certain conditions, experimental observations can be related with the prior knowledge on ferroelectric material properties to get information on some of the non-observed properties, and then they can form and demonstrate some of the linear causal mechanisms that may exist between those non-observables as well as whatever they were seeing under with the piezo force microscopy data. So now my Gandalf hat comes into play, and I'm thinking, well, I have all of these models, and I have all of these papers that I read all the time, where people are looking into correlative nature of the frameworks and of the target properties and the descriptors. Is there any way, and is there any problem that I can even think of where these causal mechanisms would play a great role in understanding a property? So I had a little bit of experience with working on perovskite systems, and so I picked that up again. So I thought about A-side cation ordering. So let's think about it. So cation ordering is an interesting problem, because it leads to multiferric behavior in perovskite systems. So let's think about the PNMA type of structures. There is an exact cancellation of the polarization vectors for these type of structures. However, if we look into the double perovskite systems where there are two different type of A-side cations and then the A-side cation ordering is involved, there is a non-cancellation of the layered polarization. So this is a very interesting type of material systems. And for this type of systems, the polarization and magnetization is switchable via tuning the tilt and the rotational structural modes. And the nature of the ferroelectricity that is observed in this type of system is of hybrid and improper in nature. That means the structural modes are very important, and there is also a trilinear coupling that exists between the rotation, the tilt, the antiferroelectric, or the polar mode. So is there any way we can understand this a little bit better to ask ourselves the question, how do we find the building blocks that would guide us to design synthetic chemical routes, let's say to design novel multiferric systems? And in particular, if A-side cation ordering is such an important property, what are the factors that are really responsible for this in double perovskites? And that's where this study comes into play, and that's where this causal machine learning comes into play. So this workflow would seem very familiar to you because we have the data set, we have combination of different features, and then we have the target property. Our compositional space is made of the double perovskite systems. So A prime, BB prime, O6. We are considering 3D, 4D, 5D transition metal ions. And then we are considering three different A-side cation ordering, columnar, layered, and rock salt. And then we perform geometry optimization, compare different energies for different type of orderings, and then also look into the symmetry and structural distortions. Next is the compilation of this feature space like structural modes, and then we also have the geometry-driven descriptors. And then this is where we want to investigate more of the relationships which are correlative as well as the causal that would directly tie us to the cation ordering. So here is a sneak peek into the data set. So as I've mentioned, we are considering three different types of ordering: A-side, layered, columnar, and rock salt. And then we are fixing the B-side ordering to be the rock salt, and the G-type AFM magnetic ordering was utilized because for this type of system, the G-type AFM almost has always the ground state. And for the, how diverse this data set is, you can see by looking at the different combination of the charge states of the BB prime and A prime that we consider also with respect to the tolerance factor. Now let's look into the distribution of various structural modes. So we are considering the rotational modes, the tilt, the antiferroelectric, A-side, and the O-side displacement, as well as the charge disproportionation mode in the 2D and the 3D. So just by looking into the distributions, we can already say that some of these modes are, let's say, present in a specific type of ordering versus it's absent in a specific type of ordering. So this type of structural modes and including them in the descriptor space is very important, which we can already conclude from this. And then comes the next set of machine learning models that we build in. I'm utilizing random forest model, and we construct a series of models utilizing a different set of descriptors. So combining the geometry driven with the structural modes, and then having the target to be either classifying into columnar rock salt or layered ordering, as well as sometimes only just if it can form the clear layer ordering or not, and then the energy differences. And we can also very well find the important features that are associated, which almost relate to all of the structural modes, as well as some of the cation radius, and then the energy differences. Now, with this, we can get like all sorts of models with like extremely high accuracy, like 94 or 98% accuracy. And you can look it up in the archive version of the paper that we have the confusion matrices and all. Then I ask myself the question, is that all? Because are we predicting the cation ordering for all of the materials with the same accuracy? And that is not true, because if we just look at the probability distribution even, you can see that some of these materials will not have the same probability score or the confidence bound. So that's what we have introduced in this particular study, how we can look into the assigning the confidence bound for each type of prediction that we perform, even after doing the traditional ML, like random forest classification or regression type of model. And then the next is the causal networks. So once we have this type of models done, we already are recognizing the fact that these features are correlated in nature and they are correlating to the target property. But how one feature is affecting the other, that is not being quantified, and that is not being said by just looking into the correlative nature. So that's where we introduce these causal networks to look into. Let's say we want to classify between the columnar or the layered or rock salt, or clear layered or versus not. And we see for some of these, so let's say for columnar or layer type of ordering, the tilt mode drives the other descriptors, such as such as displacement at the A' sites and the charge disproportionation modes towards the target. And these are the linear causation models, so we can also quantify the effects of the positive and the negative causations. Another point that we could relate to from the physical interpretation, that as I have mentioned in the very beginning, that the tilt, the polar mode, and the rotation mode establish a trilinear coupling in the Landau free energy expansion. And for one type of specific cation ordering, if there is an absence of the rotation mode, then these modes, the other two modes, will not couple with each other, and that can be signified by the negative causation effect. And from here, we can also say that we can increase or decrease this mode amplitudes, and that would be very interesting to see when we have, let's say, the temperature dependence or the disordered structures more into the systems, how we can directly tune the exhibition of different type of cation orderings in double perovskite systems. So here is sort of the summary, where we have found the structural modes to be very important, and we can also pinpoint what are the charge, let's say, what are the charge states of combination that we can pick for exhibition of polar phases. And then also we have introduced some of these nonlinearity in the feature space, and that could be related to the energy differences of formation of clear layered ordering. If we only consider the structural modes, we can still build some sort of a good model. However, the geometry-driven descriptors are also very important. And these are sort of the crucial information towards the rational design of hybrid improper ferroelectrics, which we couldn't have understood if we wouldn't be combining the causal ML, the symmetry, and the DFT calculations all together. This is under review now, so you can also take a look at the archive posting